Assalamu alaikum. Today we are going to see the chapter about modeling and the energy method. We saw how to get the equation of motion of the system using the free body diagram. Today we are going to see another method to find the equation of motion of the system using energy concept, and how to find the natural frequency for the system. So an alternative way to determine the equation of motion and an alternative way to calculate the natural frequency of a system. Useful if the force or torque acting on the object or mechanical part are difficult to determine. So sometimes we have a difficult system. So we are going to see that using energy we can get the equation of motion of the system more easily than the usual one. So potential and kinetic energy. The energy in the system are potential and kinetic energy. So if we have elevation, so we have potential energy, and if we have motion, we have kinetic energy. So the potential energy of mechanical system U. So U is the potential energy. You see here. Is often stored in the spring. So the potential energy is usually in the spring. So if we have a spring in the system, we have a potential energy. Remember that the force in the spring is F equal to Kx. Now U spring is by definition the integration from 0 to x0 f dx. It will be the integration from 0 to x0 kx. So f is kx, f here it's kx dx. So when we make an integration, we get half kx0 square. So this is the potential energy in the system. So we have the system here, m, the mass, the spring, and x0 is the position here. X0 is 0, so it's a reference. So the displacement of the mass is described by x0. The kinetic energy of mechanical system T, so T is the kinetic energy, so U is the potential energy, T is the kinetic energy, is due to the motion of the mass. So T translation, if you have a mass translation, so half of mx dot square. So it's half of the mass multiplied by the velocity squared. If we have rotation, we have the kinetic energy half j theta dot square. So j is the moment of inertia, and theta dot is the speed of rotation. Conservation of energy. So for a simple conservative, that means no damper mass spring system, the energy must be conserved. So when we have no damper in the system, we have conservation of energy. That means the potential energy plus the kinetic energy are equal to constant. So the sum T plus U is constant. Or if we make derivative with respect of time, since T plus U is constant, so the derivative with respect of time of T plus U, it will be equal to 0. So this is another equation of Lagrange. So at two different times, T1 and T2, the increase of in potential energy must be equal to the decrease of kinetic energy, or vice versa. So U1 minus U2, which is the potential energy, is equal to T2 minus T1, which is the kinetic energy. So this is in terms of a change of potential energy, it will be equal to the change of the kinetic energy. And we can get that U max, which is the maximum value of potential energy, will be equal to the maximum value of the kinetic energy. So this is another equation. Now we can derive the equation of motion from the energy. So we have the same system. We have a mass here, we have a spring, and we can write our equation, the derivative with respect of time of T plus U. It will be the derivative with respect of time of the kinetic energy and the potential energy. So we make the derivative with respect of time. We get from that x dot is m x double dot plus kx. So since kx is 0 cannot be equal to 0 all time, so we have mx dot plus kx equal to 0. So here we get at the end, using the energy concept, we can get the equation of motion that we saw before using the free body diagram. So to find the equation of motion, we have to make the derivative with respect of time of the kinetic energy plus potential energy. So we get the equation of motion. Remember that for the mass spring system, the kinetic energy half mx dot square, that's mean half of m multiplied by speed square, plus half of kx square, which is the potential energy, which is stored in the spring. Determine the natural frequency directly from the energy. Now we are going to see how to find the natural frequency using the concept of energy. So if the solution is given by x of t equal to a sine omega t plus phi, this is the solution of the system. We assume that it's given by this equation. Then the maximum potential and kinetic energy can be used to calculate the natural frequency of the system. So U max, which is the potential energy, it's equal to 1 over 2 k a square. So this is the maximum value of potential energy. Here we substitute x by a because the maximum amplitude of x is a. So it's a k a square. This is the maximum value. For the kinetic energy is half mx dot square. So when we calculate x dot square, x dot here, we get a omega as maximum value of the speed. So a omega is the maximum value of the speed. So the potential, the kinetic energy will be half m omega n a square. Since these two values must be equal, we have in the previous slide we said that U max is equal to T max. So we can equate both terms. Half k a square equal to half m omega n a square. So we calculate k from this equation. K, it will be m omega n square. So omega n will be root square k over m. So from this equation we get that omega n is root square k over m. So when we have a system mass spring, the natural frequency is given by this equation, and it's found. We can find it using the free body diagram, and you can find it using the energy concept. Another example here, compute the natural frequency of this roller fixed in place by a spring. Assume it is a conservative system, that means no losses, and rolls without spring. So here we have a disc, for example, attached to the spring, and when the disc rotates, and the displacement of the spring is noted by x of t, and the rotation of the system is noted by theta of t. R is the radius of the disk, and m is the mass of the disk, and j is the moment of inertia of the disk. So t rotation, here we have a translation and rotation, so we can calculate the kinetic energy of rotation is half j theta dot square, and t translation is half mx dot square. So this is two, we have in the system two kinetic energy. One is of rotation of the disk, and one is the displacement of the disk. Now for the so x in the system is r theta, so we can, there is a relationship between r and theta. X dot is r theta dot, so x dot is r theta dot. So t rotation is half j x dot square over r square. From this equation we substitute theta dot by x dot over r. So we get t rotation is this equation. The max value of t happen at V max. So we said that the maximum value of kinetic energy happens at V max. So V max is omega n a. So T max here, T max will be half j omega n a square over r square plus half m omega n a square. So this is the value of T max for the system, rotation plus displacement. So we can rearrange the equation and we get half of m plus j over r square. Omega n square a square is the maximum value of the kinetic energy. Now for the potential energy, since we have a spring, so the potential energy is U and happen at x max is A. So U max is half x A square plus T max equal to U max gives us, we equate both quantity. We have this is for T max, this is for U max. So from this equation we get omega n is root square k m plus j over r square. So this is the natural frequency for the system described by a disk attached to the spring, and when it's rotating there is displacement x. Now another example to determine the equation of motion of the pendulum using energy. So we have a pendulum. The length of the rod here is L. The mass is attached to the rod. The position of the rod is described using theta, which is the angle between the vertical axis and the rod. And here J, which is the moment of inertia, is ml square. We have of course the mass of the spring, the mass here, the weight of the mass mg, and we are going to find the equation of motion of the pendulum. As you see here, if you use the free body diagram, it's very difficult to find the equation of motion. So we are going to use the concept of energy to find the equation of motion. It will be more easy. So the kinetic energy is half j theta dot square. It's half ml square theta dot square. So this is the kinetic energy. The potential energy mgl 1 minus cos theta. The change of elevation, because there is elevation when the pendulum is moving, there is elevation, is described by L 1 minus cosine theta. So this is the elevation of the pendulum or of the mass when it's moving. So it's mg z, z is L 1 minus cosine theta. Now we make the derivative with respect of time. We assume that there is no loss of energy. So the derivative with respect of time of t plus u will be equal to 0. And what is the derivative? It will be the derivative with respect of time, half ml square theta dot square plus mgl 1 minus cosine theta. That's mean we group together or we add together the kinetic energy and the potential energy, and after that we make the derivative with respect of time. Now we continue the derivation. So ml square theta dot theta plus mgl sine theta theta dot equal to 0. We put theta in the factor, so we get ml theta dot square plus mgl sine theta equal to 0. So since theta dot cannot be equal to 0 all time, so this quantity should be equal to 0. So we get ml square theta dot theta double dot plus mgl sine theta equal to 0. So here this is a term, nonlinear term. So we can approximate sine theta when theta is small by theta. So we get theta dot t plus g over l sine theta equal to 0, and theta is very small. So we can substitute sine theta by theta. So we get theta dot t plus g over l theta equal to 0. So g over l, it's omega n square. So omega n for the pendulum is g over l. So this is the natural frequency of the system, and this is the equation of motion of the system. Equation of motion. Here we are with the assumption that theta is small, so sine theta will be equal to theta. If theta is big, so we cannot make this approximation. So this is it's out of scope of our system. This one also. Lagrange method for deriving equation of motion. So again, consider conservative system and its energy. It can be shown that if the Lagrangian, so L is called Lagrangian. That's why we call Lagrange equation. Lagrangian L is defined by L is T minus U. That's kinetic energy minus the potential energy. So in this case, then the equation of motion can be calculated from the derivative with respect of time of the partial derivative of L with respect of Q dot minus the partial derivative of L with respect of Q is equal to 0. In our case here, for a translation system, Q is equal to X. For a rotation system, Q is equal to theta. So just its a notation. It's theta, so Q in the rotation system is theta. So which becomes the derivative with respect of time of the partial derivative with respect of Q dot minus the partial derivative of T with respect of Q plus the partial derivative of U with respect of Q is equal to 0. So this is the Lagrange equation. Assuming there is no damper in the system, we are going to see the damper. When we have a damper, what happens to the system. And Q here is called generalized coordinate, and we said that if we have translation, Q is X, and if we have rotation, Q is theta. Now let's make an example. So derive the equation of motion of a spring mass system via the Lagrange. So we have to calculate the kinetic energy. We said that the kinetic energy is given by this equation, and the potential energy is given by this equation. The potential energy in the spring, it's stored in the spring, and kinetic energy is in the mass because the mass is moving. Here we have, as I said, Q is X, and the Lagrangian becomes L is T minus U is half mx square minus half kx square. And if we make the derivative with respect of time and x dot, we get the derivative with respect of time of delta t over dx dot. Here we get the term mx double dot, this quantity. Delta t over dx, the kinetic energy, it's not, there is no x in the kinetic energy, so this will be equal to 0 for our system. Du over dx, here we get kx, the quantity here, it's kx. So it will be delta t over dt mx dot minus 0 plus kx. So we get at the end the equation of motion given by this equation with what we have using the free body diagram. So as you see, using Lagrange equation, we can easily find the equation of motion. And of course, if we divide the mass, do the equation by the mass, we get x double dot plus k over mx equal to 0, and this is omega n squared. So it's easy to find the equation of motion using the energy concept or Lagrange equation. More on spring and the stiffness. So we are going to see more details about spring and stiffness. It will be in the second video. So go to the second video to see the rest of the presentation. So see you in the second video.